So we've generated our power series representation for our natural exponential function centered about x equals 0. Let's do the same thing for the sine of x. Find a power series representation for the sine of x centered about x equals 0. Well, f of x is derivative on down. F of 0 clearly is this. F prime of 0 is this. Here is my f double prime of 0. Triple prime. Fourth order derivative. Fifth order derivative, again evaluated at x equals 0. Notice I alternate from 0 to some constant, but ignoring those constants, I misspoke, ignoring the zeros, those constants alternate between 1 and -1. So it looks to me like f evaluated 0 is just gone, but f prime of 0 is just 1. F double prime of 0 is 0, so that whole term drops out. My f triple prime evaluated 0 is -1. The fourth order derivative evaluated there is 0. My fifth order derivative evaluated there at 0 is simply that. So it looks to me like my power series representation looks like this. And I showed you on a computer screen what that really does in terms of the graph of the curve. So the first term, that first powered or first degree Taylor-Polynomial representation for f is nothing more than a tangent line at x equals 0 to the graph of y cosine of x. There is the best fitting third degree polynomial, approximated curve about x equals 0. And there's a fifth degree polynomial. Now, of course, right into summation notation, I guess I should take a peek at these terms to see if I can't come up with some kind of general description. So how about this? N equals 0 and up. Fractional coefficient, 2x raised to the power. Looks to me like the power is a linear progression where the slope is 2. But I want this to be the term I generate when n is equal to 0, whose exponent is 1. But when I plug in 0 in for n here, that's 0. So what do I add to 0 to get positive 1? Well, positive 1 itself. Now, as far as my denominator is concerned, notice what's being factorial is the same as the exponent. And notice how I have a sign change in each and every term. So it looks to me like my numerator is going to be this, I think, but I might have a sign error. Let me double check it. When I plug 0 in for n, it's positive. But when I plug 0 in for n, here's a term and it's positive. So I know I should not change that to an n plus or minus 1. So you and I have just generated the power series representation for a sine function centered about x equals 0. In a very similar fashion, you on your own can show this or derive this. I won't because it's so similar to what I've just done. It's the same thing. The only difference is I don't have a plus 1 here or here. So if you want to take a peek at what that looks like in expanded form, it's just my first term, which is positive 1, minus a 1 over 2 factorial x squared plus a 1 over 3 factorial, oops, I misspoke. I meant 1 over 4 factorial. X to the 4th and on. I'm running out of room to generate the nth term, but the nth term is simply this and this for these two functions respectively. Now, the author of your text or any other text for that matter might have some other basic functions with which they list the power series representation. Personally, I think these are the big three that you should remember. In particular, they just kind of come in handy when we solve differential equations. Not this semester, but certainly we dive into Math 33. All right, good list. I'll try to put it to practice.